RLC circuits. Notice the name RLC, that means you have resistors, inductors, and capacitors in it. So this is the circuit that we have. We have 300 ohm here on the top. We have a voltage source of 150 volts right here. We have a switch down here that's open. It will close at t equals to 0. I have an inductor here of 5 millihenry. I have another resistor here of 200 ohms. And I have a capacitor of 20 nanofarad. And the question, find the expression for the voltage across the capacitor at t for t greater than 0. So this is V sub c. And the question, find V sub c as a function of time for t greater than 0. Just like RL and RC circuits, the first step I'm going to do is I'm going to look at the circuit for t less than 0, and I'm going to try to find the voltage across the capacitor at 0 minus, and the current through the inductor is 0 minus. That's the process I'm going to use. I'm going to look at the circuit for t less than 0 and try to find the voltage across the capacitor at 0 minus and the current through the inductor at 0 minus. So we're assuming this circuit been in that position, the switch open for a few minutes. Few minutes consider a long time. That means my circuit will look like this. 300 ohm. Plus to minus 150. The inductor will behave as a short circuit to a DC source. The switch is open. This is the 200. And the capacitor behaves as an open circuit. So the voltage across the capacitor is going to be the same thing as the voltage across that resistor. So if I know what the current through that, our book define I sub L, by the way, the current coming down. In the problem there, they define I sub L, the current going that way. So you only have one source, minus to plus, going to force the current to travel this way. Let's call that I, not I sub L. I and I sub L, the same thing except what? Opposite in sign. If you do KVL in that one, that's negative 150 plus 300I plus 200I is equal to 0. 500I equals 150. What's I equal to? 150 over 500, which is 0.3 amps.
So that'd be 30 milliamps.
Move the decimal point 2 places. 300 milliamps.
100 milliamps.
Yep. Yeah. So that means I sub L, we say we need to find the current. So I sub L is going to be what? At 0 minus. It's negative 0.3 amps, which is the same as I sub L at 0 plus. Remember, the current through the inductor does not change in 0 time. I'm going to need that one. The voltage across the capacitor is 0 minus. That's the voltage across the 200 ohm resistor. That's this voltage. 200I. 200 times 0.3, which is what? Is that 60? And that's the voltage across the capacitor, 0 plus.
Is there ever a circumstance where the voltage at 0 minus is not equal to 0 plus?
Not across the capacitor.
Not across the capacitor?
Nope.
Okay.
And the reason for that, I equals C dVc dt. That tells you the voltage cannot change in 0 time.
Okay.
So that's what we have there. So all of this, we can get these two numbers. We're going to need them later. Now we're going to look at the circuit for t greater than 0. Now the switch is going to swing down. It's going to short that side. So this is what we're going to have. And here's VC, and I sub L. I sub L is this current coming down, and VC is this voltage. Now, I can do KCL here at this node. That's one node. Actually, it goes up if you want to. If you want to include that with it, that's still the same node, you know? So this voltage here is VC, all of that. If this is ground, this is VC. Let's call this current I sub R. Let's call this current going down I sub C. On the top, what do you want to call that current going in? I sub Z. So all the currents entering that node should equal all the current leaving that node. What is going to that node? I see I sub Z going in. And what's leaving that node? I sub L plus I sub R plus I sub C. Let's write I sub Z. That's what? This voltage minus that voltage Now, what's this voltage here? Well, try again. Oh, I'm sorry.
Are you taking a test?
Nope.
All right. He's gonna come in and just get some footage of you teaching.
Sure, come on in.
So just act natural. He's just finishing up a phone call.
Okay.
But that's cool.
You like that?
Yeah.
You guys gonna be at the graduation. You're gonna be at the graduation picture. Video.
Cool.
Let's go back. Yes. Or stretching?
Yeah, sorry.
Oh, I have a question. Joan, you have a question on this? Go ahead.
I do.
You
I
don't-
like that shade of red you've used.
Okay, I'll use black and blue. I can use a darker one. How is that? How you doing?
Hi, how are you?
Good, thank you.
So we show a video at commencement every year. It's just kind of a review of the year. So we stop in and get little snippets from classrooms. Hey, that's really cool.
You like that?
Yeah, I like that. Rick, do that again.
When
You see his hand in there. That's kind of
yeah,
cool.
that's nice.
You know.
These actually, you're live now, by the way, Joan. You're on video. It's gonna go on YouTube. For real. I put all my videos on YouTube, so while we're talking right now, that's going
Erase
on.
that one of me dancing in the riverfront.
Oh no.
I don't want to know about that.
So if this is ground, what's this voltage here? VC, right? So what's this voltage here then? This one says this end is what? 150 volts higher than that end. This is 150 higher than that end. So this voltage is what? VC plus 150. This is VC here. So what is I sub Z? It's this voltage minus that voltage. VC plus 150 minus VC divided by 300.
So it's 150.
Yep. Equals. What is I sub L? That's this current here coming down. It's this voltage. Well, we can't do this voltage minus this voltage divided by R because we don't know what R is. So what is V? L equals what? We know V equals what? L di dt. So what is then I equal to? 1 over L, the integral of V dt. So if I use that for the inductor, it's 1 over 5 millihenry. The integral of the voltage, which is VC, that's the only voltage across that. The voltage here is the same as this here, the same as that one. Plus, what's I sub R? It's this voltage minus this voltage divided by 200. So what's this voltage? VC minus 0 divided by 200 plus, what is the current here? The current through a capacitor is what? I equals C dVC dt. C, which is 20 nanofarad dVC dt. It looks like a beautiful equation, huh? And now we're going to solve it. VC plus 150 minus VC is what? 150 divided by 300. What is that? 0.5? Yep. 0.5 equals 1 over 5 millihenry. Let's see if we can do the math. 1 over 5, 10 to the minus 3. That's 200. The integral of VC dt. I'm just getting lazy now. I'm not putting the t there. Plus VC over what? 200 plus 20 nanofarad dVC dt. We don't like to see integration derivative in one equation. How do we get rid of the integral? We take the derivative. Yep, bye-bye. We take the derivative. So what is the derivative of 0.5? 0. What's the derivative of the integral? They cancel each other out. What's the derivative of this? 1 over 200 dvc dt plus 20 nanofarad, the second derivative. Let's divide everything by 20 nano. Nano is what? 10 to the minus 9. So 0 equals the second derivative (1 over 200) divided by 20 e to the negative 9. 250,000 dvc dt plus 200 divided by 20 e to the negative 9. 1 times 10 to the 10th Vc. And now that fits the format that I have. Here's the format. If you have a second order differential equation that looks like this, figure out what alpha and W is, and based on that you can decide what the solution is. When alpha is bigger than W, that's called overdamped. When alpha is less than W, that's called underdamped. And when alpha equals W, it's called critical damped. So I need to know what alpha and W is before I decide which one of these is the solution. One of them is going to be the solution. So let's see. That means this piece here is 2 alpha. 2 alpha equals 250,000. Which means alpha equals what? 125,000. W squared equals this. W equals the square root of that, which is 10 to the 5, and that's what? 100,000? So which one's bigger? Since alpha is bigger than W, my solution for that, the voltage across the capacitor, a function of time, it's going to be, ready for that? K1 e to the power of negative alpha plus alpha square root alpha squared minus W squared t plus K2 e to the power negative alpha minus alpha squared minus W squared t. Let me see what alpha squared minus W squared is. 125,000 squared minus 100,000 squared. Take the square root of that number. This is 75,000. This piece here is 75,000. So it's going to be K1 e to the power negative 125,000 plus 75,000 negative 50,000 T plus K2 e to the power negative 125,000 minus 75,000. Negative 200,000. That's the voltage across the capacitor. That's it. There's only one little problem. K1, K2. We need to find K1 plus K2. Or K1 and K2, not plus. I don't like the word plus here. And K2. If I know what they are, problem is history. Let's go back to page 1 when we started the problem. I found the voltage across the capacitor as 0 plus to be what? 60. Remember that? Let's go to that equation. This is K1 here. Voltage across capacitor 0 plus equals 60, which equals K1 e to the power of 0 plus K2 e to the power of 0. K1 plus K2 equals what? 60. One equation, how many unknowns? 2. I need another equation. To get the second equation, here we go. Let me write this one here. I need to find the derivative at 0. I need to know what the derivative at 0. But I need it both places, both ways. What do I mean by both ways? One from the circuit and one from the equation. And I will set them equal to each other, and that will give me my second equation. So this is EQ1. To get the second equation, I need to know what the derivative of the voltage at 0 from the circuit and from the equation. While we're doing the math, I'm looking at the equation right here. Let's take the derivative of that. So here we go. Let's do the derivative from the math. From the equation. This is the voltage. What's the derivative of that? Not at 0 at any time. Negative 50,000 K1 e to the negative 50,000 T minus what? 200,000 K2 e to the power of negative 200,000 T. What's the derivative at 0? Let T be 0. That's what? Negative 50,000 K1 minus what? 200,000 K2. If I know what the answer to this, if I know what that as a number, that's my second equation. So if this was a number, then I have two equations by two unknowns I can solve for K1, K2. So how can I change this to a number? That's when I go back to the circuit. So let's go back to the circuit. Let's look at V C at 0 plus. Let's look at the circuit at t equals 0 plus. And what is that voltage? And what's the derivative of that? At 0 plus. So at 0 plus, this is what my circuit looks like. We did that and we have the equation for it. It looked like this. Not this one. What was it? At 0 plus. Right here. That's my circuit. Five millihenry. 200 ohm, 20 nanofarad, 300, 150. Let's see what we know at that time. At that time, we know there was a current going upward. There was a current going this way of 0.3 amps. Where's that? We did that early. Where was it? First page. That current through the inductor is 0 minus, the same as 0 plus. I had the current coming down of negative 0.3. That means it was going up at 0.3 amps. Right here. I also know the voltage across the capacitor at that time was what? 60. So I know the voltage here is 60. If this is 60 here, this is 60 here, this voltage is what? 150 plus 60, 210.
That's the voltage.
Yep. Because this was 60 volts. We also know what this current at that time. How do we know what that current? What is I of the 200 ohms? We know the voltage here across that at that time was 60 divided by 200. Is that 30 or 0.3? What is 60 over 200?
Yeah, 0.3.
0.3? We know what this current is. 210 minus 60, which is 150 divided by 300. Point 0.5, right? So if I do KCL at this node again, KCL, it says the current in, which is 0.5 amps going in, equals the current, or plus, this is going in, I made it going in, right? Plus the 0.3, that's this current, should equal the current leaving, which is this one, plus, what's the current? I equals what? C dVc dt. The 0.3 cancel each other out. 0.5 divided by 20 nanofarad equals the voltage across the capacitor is 0. One, two, three, 4, 5, 25 million, I think. Now I'm in good shape. Remember what I said early. I need two equations by two unknowns. I have one. I have this. I need another one. Bless you. I said if I know what the derivative of the voltage at 0, if I know what that number is, I'm done. Well, I found what that number is. I found this from the math, but I found this from the circuit. That's what that number is. So if you plug it in here, that's your second equation. So 25 million equals negative 50,000 K1 minus 200,000 K2. Let's divide everything by negative 50,000. Shrink the numbers. K1 plus, is that 4? Equals. Must be a way to erase that. How you erase it? What was that? 25 mil. 1, 2, 3, 4, 5, 6 divided by 50,000. Is it 500?
Yep, negative 5.
Yep.
Negative.
That's my second equation. EQ2. My first equation, I have it with me here. K1 plus K2 equals what? 60. Now let's solve them. Two equations by two unknowns. I can use the elimination method, which means what? Multiply this by negative 1.
Wait, hold on. How did you went from negative 500 equals K1 plus 4K2 to 60 equals...
That's the first equation.
Oh, that's the first... Oh.
Yep.
I thought you were taking the
No.
equation, making it down.
If you multiply by minus 1, the bottom one, the top one stays negative 500 equals K1 plus 4K2. Negative 60 equals negative K1 minus K2. Elimination method. Negative 560 equals what? 3K2. K2 equals 560 divided by 3. And 2/3. Negative 186.7. If I know what K2, can I find K1?
Yep.
K1 minus 186.7 equals 60. K1 equals what? 246.7. And finally, I get the answer. What is the voltage across the capacitor at any given time for t greater than 0? Here we go. VC as a function of time for t greater than 0 is K1. K1 is what? 246.7 e to the power of negative 50,000 t minus 186.7 e to the power of negative 200,000 t. Instead of saying for t greater than 0, that sometimes you see u sub t. Because what is u sub t? Has a value of 1 when t is greater than 0, 0 when t less than 0. So for t greater than 0, that's what the answer is. Or you might say just for t greater than 0. The only problem with by putting u sub t here, For t less than 0, this will give me a value of 0, which we know the voltage across the capacitor was not 0 at that time. But a lot of times you see the book do that. Instead of t greater than 0, you see u sub t. Not in this case.
T has to be really small though.
Huh?
T has to be really small.
Yeah, t will have to be a very small number. Otherwise, well, it doesn't matter any because I'll go to 0 quickly. Yeah. And that's that problem.